This is the Pilot Landing Assistant designed by Ryan Densberger and Daniel Calvo for our senior design project at San Jose State University, spring 2010. The Pilot Landing Assistant can assist a pilot in landing training or refreshing landing skills by graphically giving the pilot all the necessary information about the landing in real time. Flight training is expensive, and landing is the hardest skill to learn. Therefore, a training aid would allow students to learn proper landing technique faster and cut down on training time and cost. The Pilot Landing Assistant consists of a hardware sensor which mounts to the underside of the aircraft and is capable of measuring the aircraft's airspeed, altitude, and orientation, and wirelessly transmit information via Bluetooth to a graphical display in the cockpit. The sensor unit was designed via solid modeling software and CNC machined out of aluminum. Its unique dome assembly allows the rangefinder, which measures altitude, to always be pointing perpendicular to the ground for greater accuracy. The software has a graphical and digital mode for the pilot with large color-coded displays to communicate the information without needing the pilot's direct attention so they can focus on flying the airplane. Future renditions of this display might become heads-up display units, which have the ability of projecting images on the windshield to be more in the pilot's peripheral vision. The components of the sensor unit are CNC machined out of aluminum. On the base, we have mounted two triangular supports which attach the dome and allow it to pivot back and forth. Inside the dome assembly, we have an ultrasonic rangefinder which is used to measure the altitude. Connected to the dome is a small servo. Through connecting linkage, connects to the mounting bracket of the ultrasonic rangefinder. A main servo is attached to the main servo bracket, which through mechanical linkage connects to the dome ring. If you look at the bottom, we can see the dome protruding from the base. Inside the dome, we see the ultrasonic rangefinder. If you look at the back, we see the features such as the master on-off switch, the status LED, the processing LED, the connection LED, and the antenna for the Bluetooth transmission. Over here we see RAM and static pressure inputs to the differential pressure transducer. Okay, so this is going to be a brief tour of the sensor unit for the Pilot Landing Assistant. Inside we've got 7 major components. Up here is our IMU, which measures inertial forces to calculate the unit's pitch and roll. We've got our main controller here, which reads information from our IMU, our differential pressure transducer, and our ultrasonic rangefinder, so that we're able to get orientation, airspeed, and height. Right here is a Bluetooth transceiver, which we use to communicate the information to our host. Finally, we've got 2 servos. We've got a small servo here, which controls the position of the rangefinder for roll compensation. We've got a larger servo here, through this mechanical linkage, controls the pitch of our dome assembly for pitch calibration. If we look at the back, we've got a number of features. Over here are the barbs for the hoses to attach ram pressure and static pressure for the differential pressure transducer. We've got our master on-off switch. We've got a status LED, which is red if the unit is calibrating and green if the unit is ready for operation. We've got our antenna. We've got a processing LED, which blinks if the unit is processing data. And below here we've got our connection LED, which is also 2 colors. It's red if it's not connected and green if it is connected. If I turn the switch on, we're calibrating, which can be seen on the IMU itself. It's in calibration. We're not connected and we're not processing data. Once the IMU is done calibrating, it's going to trigger the rest of the system, and there we go. Now we are calibrated, we're processing data, however, we're still not yet connected to anything. Looking inside, we can see this light flashing says that our Bluetooth module is in Discover mode, so if we were on a host, we could find it. We could also see that the dome is now responding to position changes. The dome assembly was designed to allow up to plus or minus 20 degrees of pitch compensation and plus or minus 20 degrees of roll compensation for the rangefinder. This is to accommodate any type of landing scenario, including side-slip crosswind landings, to ensure that the rangefinder remains perpendicular to the ground. This is the Pilot Landing Assistant software package. As you can see, there are two modes, a graphical mode and a digital mode. In the graphical mode, we've got 4 displays, 3 of which are indicators, and the last one here is a monitor, which we'll get to in a second. The first indicator on the far left here is an altitude indicator, and what this is a bar graph that displays the height of the aircraft above the ground. There are 3 resolutions for this altitude indicator. Right now you can see it's 0 feet to 5 feet. The altitude indicator bar consists of 3 colors. Blue indicates that the aircraft is 25 feet to 15 feet. Yellow indicates that the aircraft is 15 feet to 5 feet. And red indicates that the aircraft is 5 feet to 0 feet. This allows a pilot to get a very good understanding of how high they are off the ground using their peripheral vision. The second indicator is an attitude indicator. This little aircraft in the middle here will actually pivot based on the aircraft's orientation. Each notch here is 10 degrees. The last indicator is a speed indicator, which denotes the airspeed of the aircraft. It's in knots. This indicator is also color-coded. It is programmed for a Cessna 172, which has a stall speed of 40 knots. If the airspeed is above 40 knots, the airspeed will be indicated in a green color. As soon as the airspeed drops to 40 knots or below, it will change to a red color. Finally, we have the attitude monitor. This isn't just a simple representation of what sensors are reading. This is actually a calculated value based on an algorithm that was programmed for a Cessna 172. As you can see in this monitor, there's 2 bars, one blue and one red. The way that this monitor works is it takes into account the aircraft's airspeed, the aircraft's pitch, and the aircraft's altitude, and it determines whether or not the orientation of the plane is appropriate for a landing. For example, let's say that an aircraft is in perfect landing orientation except it is too high off the ground. As the aircraft slows down, the nose will want to drop, so the pilot must apply back pressure to keep the nose up. If the aircraft is too high off the ground, the aircraft could stall and fall to the runway. Therefore, the attitude monitor would show excessive nose up in that situation. What if the pilot was coming in too fast or too slow? The attitude monitor would show aggressive nose up if the pilot was too fast, or not enough aggression if the pilot was too slow, given the aircraft was at an appropriate altitude. The idea is to make a landing with the attitude monitor bars as close to the middle as possible. We also have a digital representation for pitch, altitude, and airspeed. The numbers in here are simply the numbers sent from the sensor array. Down here is the user controls for the software. Here's where the user can set the COM port. For example, we can set COM 2, and we have a little indicator window here telling us that the COM port was set. We also have a calibrate button, so if we look at the digital values after we mount the unit to the aircraft, whatever these values are supposed to be our offsets. Once we hit calibrate, these will all zero out. Finally, we have the controls for the communication. Once we set the COM port, we can hit the run button to actually begin the communication, or hit the halt button to terminate the communication. So this is the software package for the Pilot Landing Assistant.
Now we're going to show the connection between the hardware and the software of the Pilot Landing Assistant. On the hardware, you can see that we are calibrated, we're processing data, but we're not connected. We go over to the software and we put in the COM port, which is currently connected to our Bluetooth device, in this case COM28, and set that. We can see that our COM port is set. If we hit the run button, you'll notice that the connection light will change from red to green as soon as the communication is established. There we go, and we can see that communication is achieved and PLA is running in our little message box. And we can see our default values all went away and we're actually reading processed data. Now if I actually pick up the device, you can see on the screen that the software mimics what the hardware is doing. You'll notice that the altitude indicator is kind of finicky right now. That's simply because it's ultrasonic and it's reading reflections from the wall and whatnot. Also, you'll notice that the airspeed, if we change the airspeed, will update. If we go over to the digital side, you can see all the digital values being read right off of the sensor unit. You can change the airspeed here too. Change the altitude and the pitch. We go to calibrate. We can take the current orientation, define it as 0. We go back to graphical.
This demonstrates the altitude indicator. We can define the current configuration as 0 by clicking the Calibrate button. Then we can see the altitude indicator change as the sensor unit is raised and lowered. Notice that the attitude monitor is incorrect due to the fact that our variables such as pitch and airspeed are inappropriate for a valid result. The unit is currently being powered by its internal 7.2 volt lithium-ion battery, which can power the unit for up to 2 hours.
And once we're done with the communication, we can go back and hit the halt button, and you'll see that the green light turns red, telling us that the communication is now terminated. Also, you can see in the message box, PLA halted, port closed.
This is a simulation of the pilot landing assistant in operation. The full blue bar indicates that the aircraft's above ground level altitude is greater than 25 feet. Current attitude and airspeed are also indicated. As the aircraft ascends below 25 feet, the blue bar descends until it reaches 15 feet. Then it resets as yellow and indicates altitude from 15 feet to 5 feet. Finally, the yellow bar resets to red and indicates altitude from 5 feet to 0 feet. Notice that the attitude monitor displays the difference of the actual attitude from the calculated ideal.